This example uses the set covering formulation to determine the minimal number of locations for LTL terminals. Less than truckload carriers are carriers that have a network as opposed to truckload shipments. And then the question is, what is the best set of terminals that allow the carrier to cover the country? And in this example, the national LTL carrier would like to know what would be the minimum number of transshipment terminals needed to cover the continental U.S. and what are their locations. All of the existing local and pickup and delivery terminals are located near the intersection of two or more interstate highways. Since hours of service or HOS requirements limit a driver to 11 hours of driving per day, not including loading and unloading time, they would like each of their local terminals to be within 5.5 hours travel time of a transshipment terminal. And this is so that one driver can complete one round trip in a day. And for line haul operations between the transshipment terminals, they would like for all of the transshipment terminals to be within 11 hours of each other. For this example, this is a picture of what an LTL terminal actually looks like in practice. And then for our formulation of this problem, this is a script in MATLAB, and we'll be using MATLAB together with the MATLAB toolbox that has been developed for logistics engineering applications. In this script, the first cell will read in the U.S. road network, and this road network will be restricted. First, the nodes of the road network will be restricted such that their FIPS code for the node is less than or equal to 56. What this will do is restrict the road network nodes to be just those nodes that occur within the continental United States, and places like Hawaii, Puerto Rico, and Alaska will not be included as part of the road network. And then for the link constraints will be restricted to the character capital I, and that'll restrict it to just interstate road nodes. And this uses the matlog function called subgraph. And what we get then is the first output is the set of longitude latitudes for the node locations, together with the arc list representation representing the beginning, ending point, and distance in miles for each road segment between pairs of road nodes. And then the first step is that we thin the network, and we thin it so that we reduce any of the nodes that are not connected or intersections with other interstates. And when we remove the other roads, which might be U.S. highways or other non-interstate roads, those nodes will still be there, but they'll just have basically they'll be of degree 2 because they'll have one in and one out interstate node, but no other nodes. So after this thinning operation, we have removed all of those nodes from our network. And then with that indication of what our new nodes should be, we can then call the subgraph command again to redetermine our resulting road nodes. The reason to call subgraph the second time is that after the thin operation, it removes the nodes, but the remaining nodes maybe have indices that are much greater than they need to be because they include the indices of all the removed nodes. So the second call of the subgraph command serves to re-index all of the nodes and corresponding arcs so that they have the smaller network size. So after that step, the next thing that we're going to be doing is removing all degree 1 nodes. And those are nodes that are portions of an interstate road network such that the road just dead ends at a final node. In reality, it would continue on to some other type of non-interstate road. But the reason we're going to be eliminating these is that it'll reduce the number of nodes and the size of our network quite substantially if we do this step. The unfortunate side effect of this will be that there's 2 or 3 fairly significant segments of interstates that basically dead end. For example, one is 75 in Michigan that goes all the way up to Sault Ste. Marie. That portion will be eliminated. Another segment is a portion that goes south from Tampa all the way down to Naples and the Fort Myers area. Again, because that dead ends, that'll be eliminated. And this code here then is a set of commands and a while loop that'll go through and eliminate that from our road network. In practice, you'd probably want to include those longer segments, but there's lots of very short segments that will increase the size of our network. So this is a judgment call. You could modify this such that only segments that are a very short distance would be removed. So this is left as something that could be revised. And then after that's completed, we call fin again, and then subgraph again. So all of this, I'm going to go ahead and execute it. This then creates our entire road network. And then to see what this road network actually looks like, we can go ahead and plot this road network. And when we plot it, this is what we get as our final output. And you can see that all of the lines in black are the interstate road network. And all of these node or intersection locations are the candidates at which we want to locate potentially one of our LTL terminals. And we're going to then solve this as a set covering problem to be able to actually solve this particular problem. So then going back to the script, since we have distances, we need to convert those to travel time. And we're going to make the assumption that the average travel time on all of the interstate road segments averages about 60 miles per hour. In practice, if you're in a not urban area traveling on an interstate, you'll probably be going much greater than 60 miles an hour. So the 60 miles per hour is meant to be an average that includes any delays where you're caught, in a traffic jam or traveling through cities and stuff. So 60 miles per hour is a nationwide average travel speed. And then we're going to be calling the Dijkstra shortest path procedure. That is part of the MATLOG toolbox. And before doing that, we're going to convert the arc list representation, which now has travel times as opposed to travel distances. And what that does is it converts it into an adjacency matrix, which is the input required for the Dijkstra procedure. This procedure itself takes a bit of time to actually compute. So while that is computing, we can look at what we're actually going to be talking about when we formulate this problem as a set covering problem. And this is the set covering problem in its most generic aspect. And what we're trying to do is essentially define a set of objects to be covered and then a subset of covered. And what we want to do in terms of the objects to be covered, we want to cover all of the intersections in the interstate road network, because those are all the places that we want to be able to actually pick up and deliver LTL packages. But we only need a small subset of those intersections to actually have terminals. And for each interstate road network, we're going to define as a set those subsets that can be reached within 5.5 hours. And that will define the subset of the intersection nodes. And then what we want to do in terms of solving this problem is that we want to make it such that when we cover this, that we want to minimize the total number of sets. So in this case, the cost of using the set is going to be the same for any of the intersection nodes. So all of our CIs are going to be equal to 1 in this formulation. So essentially, we just want to minimize the number of sets needed to cover all of the intersection nodes. And our constraints are that we have to cover all of the intersection nodes, and then also that our variables are binary, 0 or 1 in this case. And then this is the corresponding MATLAB code using the MATLOG formulation to actually solve the problem. And we'll be actually executing this in our script to solve this problem. So then going back to our script, we can see that the Dijkstra procedure at this point is still executing. It's basically having to find what is the shortest path in the interstate road network between all of these interstate nodes. And looking here over into the workspace, you can see that there are a total of 673 different nodes. So at this point, it's just finished doing that shortest path calculation. And now we have a T matrix that's 573 by 573, and it includes the shortest travel time between all of the intersections candidates. So to formulate this as a set covering problem, we're first going to create A as a logical matrix with the size of T, and then we're going to set as true. So initially everything is false. We're going to set as true all of those travel times that are less than 5.5 hours. So with that input as our constraints, we could then call and solve this set covering problem. So we have the model formulated, and then we're going to use Gurobi, which has already been set up to run and solve this mixed integer linear programming problem. We could also use Cplex. So Gurobi is able to very quickly solve this problem. The next cell is if we were using Cplex, which we're not using, so we're not going to use that to solve. And then to plot the results, what we've done is replotted it onto this road network, and you can see here, if you look closely, that the red circles represent the locations of the LTL terminals. So this is the minimal set of terminals. The actual number of terminals are equal to 17. And we can see that by looking at the non-zero values of x, which correspond to the solution, and that length of that vector index is 17. And then we call the pplot command to actually do the plotting. And then the last step in our calculation is to check if any of the line haul distances exceed 11 hours, which is one of the constraints that we wanted to enforce. And doing that test, we see that we get a logical true result, and that just tells us that our solution is such that everything is less than 11 hours, which was our constraint. So just even though we weren't actually including that constraint in our model, it happened that given our solution, everything satisfies that. So that really helps and simplifies the solution to this problem. And this is the last cell that we executed that does that calculation. And this shows what the logical result is.